welcome to eCHO or eBPF and Cilium office hours. This is, amazingly enough, episode 89 by my count. I can't believe how close we're getting to having 100 episodes of this. It's rushing along. Amazing. So I'm very excited about the episode we're going to be doing today about stack walking. But as always, before I get to that, I'm going to run through a few headlines, what's been happening in the world of eBPF and Cilium. As always, if you're watching, do say hello in the comments. We always love to hear where you're watching from. We love to hear your questions and comments and all the rest of it. And already we have Daniel saying hello. Hi, Daniel. Hope you are doing great. So what has been happening in the last few weeks? Obviously, a couple of weeks ago was KubeCon and Cloud Native Con and Cilium Con as well. So if you weren't able to make it to Amsterdam or to catch up with it live while in the sort of virtual conference, all the videos are now available on YouTube. So you can catch up with everything that happened in KubeCon. We do also have a CiliumCon playlist. We had, as I'm sure many of you will be aware, we had the first ever CiliumCon in Amsterdam, which was absolutely brilliant. I thoroughly recommend checking out those videos. It was only half a day. It's not going to take you too long to watch those videos, but there's some really great talks there that definitely recommend. And if you want another sort of summary and a perspective of what happened, particularly around the kind of Cilium landscape, my colleague Nico, who many of you will have seen hosting eCHO episodes before and being a guest on eCHO, he wrote a very nice wrap-up blog, which I think covers lots of interesting things that happened, including the fact that CiliumCon rocked. Absolutely. All right. One other thing that caught my eye this week is some stats around kernel development, particularly the BPF subsystem development. And Stanislav has put together some statistics on who the top reviewers and top authors and top contributors are to BPF in the kernel. So this is pretty cool. There's some names in here that are really familiar to me, and I'm sure to many of you out there who are eBPF aficionados. Some of you might even see your own names on this list. So I thought that was pretty fun to see that. Hi to Rajasilan, Gateway API in Cilium for the win. Yes, Gateway API was one of the hot topics for sure at KubeCon, and we do now have support for that in Cilium for ingress traffic. I completely agree. For the win. Fantastic. All right. So that was all the kind of headlines I wanted to cover today, because we've got, I think, lots to talk about here about stack walking. So let me bring in Javier. Welcome, Javier. You are Javier Honduvilla Coto. I might even pronounce your name partly right. And you are a senior software engineer at Polar Signals, right?
Yeah, that's correct. Yeah, thank you for having me.
Yeah, no, you're very welcome. So I guess a few weeks ago, I got an email saying it would be great to talk about stack walking using eBPF and what you're doing in Parca. And then you and I had a conversation a couple of days ago, and I got very excited about all the things we're going to talk about today. This is exactly the kind of digging into the details that I absolutely love. So thanks for joining us today. I think we should start with what do we even mean by stack walking, and why do you want to do stack walking if you're profiling an application?
Yeah, definitely. So stack walking or stack unwinding, it's a process of figuring out what are the functions that were called to reach the point of the code that is being executed at certain moments, right? So for example, in profiling, this would be, for example, assuming that we have some application that has, let's say, a method called main, that is the entry point, that calls a function called A, that calls another one called B, and we are within B, and at some point we are gathering a sample. What we want is, okay, we're in B, we were called by A was called by main, right? So we want to have this trail of functions to understand exactly who is calling who, right?
And for continuous profiling, you're taking those kind of snapshots of the stack every so often, I guess, and using that to build up a picture of over time how much of time is spent in each individual function, right?
Yeah, exactly. That's exactly what we do. Currently in Parca, we do this 27 times a second. So we inspect the current point of the code that has been executed. We gather the whole stack trace, and then we send this to the server where it's aggregated and one can visualize it. So, for example, something that maybe some people that are watching this are familiar with is a visualization called flame graphs that allow you to see what are the functions that are spending the most amount of CPU time running. So we can quickly visualize, for example, areas that we could potentially optimize or areas that are waiting for I/O. And of course, there's also many types of profiles. But right now, for example, we're mostly talking about CPU profiling or on CPU profiling. So we care about what's actually consuming CPU, right? There's many other types of profiles, but that's the main one that we do right now.
Great. Just going to quickly interrupt and say hi to Russell, who's joined us. Russell's a regular viewer, so great to see you, Russell. I think actually this is going to be right up your street, Russell. So I think you've got some diagrams. I'm going to bring your screen on. So this, I think, is quite a nice illustration of how memory is used in a process. Do you want to talk a little bit about why this is important?
Yeah, for sure. So this is a little bit to understand how stack walking works in native processes, and also a little bit like some basic OS knowledge that is relevant here. So when we think about a process, right, what a process actually is, so it depends on the operating system, but generally it's a bunch of metadata and state, right? So for example, we have things such as what is the parent process of the current process that we are checking. We also have our own ID. So typically, for example, in Linux, we call this the PID, right, or process identifier. And then we have the state of the process that includes a lot of things, including the CPU registers. But something that we are very interested in here, right, is when we say stack walking, why do we call it like that, right? And the reason for this is because in native applications, these breadcrumbs and these pieces of information that allow us to backtrack back to the first function that started calling the rest of the functions, this is stored, and we then need to read this part of memory called the stack, right? But something that I want to mention here, because personally I was really confused when I started learning about how computers work, is all these pieces of memory, for example, where the code is stored or where the stack is, different files that could be memory mapped, or the heap. Yeah, they obviously start at different positions in memory. They have different sizes, and they may have different permissions, but in reality, they are all chunks of memory that come pretty much the same way. And they are typically, just to talk a little bit more about this, they're typically allocated with the mmap system call. And there's not that many things to internally down in the Linux kernel. The stack and the heap don't really have that many differences inside. Obviously, there are differences, and we are going to talk a little bit about them later, but it's a chunk of bytes allocated somewhere by the kernel.
Yeah, I think, as somebody who learned C programming quite early in my career, I think having that sort of sense of memory is, there's just a series of locations, and you have an index or an address into every one of those locations. And that's kind of it. There's nothing else really to it. And, an awful lot of what programming is doing is just sort of manipulating those address pointers and changing what's stored at that location. And that's kind of everything is built on top of that. Yeah.
Exactly.
All right. So maybe let's talk a little bit, maybe dive into that box that's just called stack there. What does a stack look like? What's the information that's contained in a stack?
Yeah, so everything that we're going to be talking about now is about mostly 64-bit x86, but it works similarly in other architectures, only that yeah, we're going to be mostly talking about x86. So in x86, there's a bunch of instructions that allow us to call other functions, and they're like the call family of opcodes. We also have ret that allows to return from a function, right? And what these two functions, what these two assembly instructions are doing under the hood, among other things, is to store the necessary information so we can go back to the previously executing function, right? So call is pushing the address of the next instruction that will have to be executed to the stack. And whenever we call ret to return, it pops that return address from the stack and it jumps to it, right? So this is like the two key pieces that allow the stack to function. Of course, we can modify the stack pointer because maybe we want to add, we want to store some stuff in the stack, some temporary variable or something like that. But typically, implicitly, the stack is modified through these two assembly instructions. And if, for example, for some simple code that I had similarly to what I described before of like having function main calling A, B, C. By the way, this example, I got it from the blog post that I've mentioned in the notes. So all these little breadcrumbs that are the return addresses that we're storing for later are pushed into the stack. And that way, once we want to return from them, they're going to be read and we're going to jump to that address. So we're going to be able to continue execution basically where we left.
Yeah, I think we can think of like the frame or a stack frame as like being the state of the information in that function. We store a copy of that state when we jump to the next function, so that when we return, we've got that state information that we can pull back off the stack again.
Yeah, exactly.
Yeah. So there's an arrow there that says, what about local variables? I feel like that's begging a question.
Yeah, exactly. So this example is, this visualization only shows the return addresses that were implicitly pushed through different call instructions. But and right now, because of the layout that we have, I mean, the data we have in the stack, we'll be able to get a stack trace, right? We only have return addresses, so we will be able to generate this stack trace that shows C1, B1, A1, and main once you gather those addresses and you run through a process called symbolization that basically converts the addresses to the symbol name, right, to the function name. But what if we have modified the size of the stack at any point, right? And this is something that happens all the time. Whenever we use local variables, we might be using stack space. So whenever that happens, this is going to be slightly more complicated, and it's not going to allow us to recover this call chain, this stack trace. And this is where some other piece of information was invented, which is called the frame pointers. So again, this is a very simple example. It doesn't have local variables, but the whole idea about this is that every single function on entry is going to basically push the current stack pointer, and then it's going to assign that variable to RBP, which is called the frame pointer. And then when the function returns, it's going to undo this. The idea here is that we're effectively building a linked list of frame pointers that allow us to get the backtrace. So even if we have local variables, even if we have other things stored in the stack, which we will, we're going to be able to recover the stack trace. So this is like a very simple idea, but it's great. It's like something that probably, I guess, early on didn't exist, and at some point it had to be invented, right? So this is something that really allows us to get stack traces in a way that is very reliable and very cheap, because we, from the point of view of a profiler or a debugger, we just need to do a couple of memory reads in the stack, right? Until we reach the bottom frame, in this case, main. So yeah, it's a great thing to have. But yeah, as we're going to discuss later, unfortunately, this is not something that we always have at our disposal.
Yeah, this is the sort of model that I have in my head when I think about, what's on the stack and how I think of a debugger working, for example. So it's a little bit mind blowing to think, well, how can it possibly work if you don't have frame pointers? What do we do instead? If like how can you even have a stack without frame pointers?
Exactly. So we still have a stack, right, with the return addresses, but we don't have these little breadcrumbs that allow us to go back to the previous frame. And here, this is highly problematic because you could say, for example, okay, I'm going to try to use heuristics, right? And I'm going to try to find things that look like addresses that could belong to the code or addresses that point to the stack. But obviously, that doesn't work very well. And it's something that, for example, some applications that deal with crashes, they do as a last thing to try, basically, if nothing else works. But luckily for us, first of all, why did this happen, right? Why frame pointers got removed if they're so amazing? And the reason is a historical reason, like many other things in computer science and in pretty much any other topic, right? Which is that back in the, I guess, 80s and 90s, most computers were 32-bit computers. And not only this meant that you had 32 bits for a word size, but also that in Intel processors, you had a very limited number of registers. I don't remember right now how many, but I believe we had 8 registers at our disposal. So by setting up a frame pointer, that meant you had significantly fewer registers, which in some parts of the code, it could reduce performance, right? Because you had one less register, you will have to spill to the stack sooner than you would have if you had one more register. So they came up with something that we're going to discuss in a second. That is like a way to store this metadata that allows us to reconstruct stacks from any point. But yeah, this is the reason why this happened, right? Later on with 64-bit x64, this is no longer that much of a problem because we have more registers. But of course, some people are still argue, right, that the more registers, the better, which is true. And some, for example, in the case of interpreters and some other applications that have like very big functions that, for example, deal with the interpreter loop, compilers tend to be forced to spill registers to the stack, reducing performance in some cases like by a lot, right?
I guess that's actually another sort of interesting question. Not all languages have to treat the stack the same way, right? It's kind of up to the compiler or maybe even the runtime to do what it wants to do with the stack, right?
Yeah, definitely. And this is the interesting thing. Obviously, there is a API, right? That is kind of like an API for binary interfaces that you have to follow in Linux, for example, to call system calls, or if you're using Intel processors to be able to call functions and ensure that no one is overriding some of your registers. And you could technically do whatever you want on the stack, but then you might not be able to be interoperable with other runtimes, right? For example, like C or C++ that follow the x86 ABI. So that's actually the reason why, for example, there's no problem in compiling some code in Rust and then linking it against C++, having SIG, and everything should work, right? Because they'll follow this ABI. But yeah, I mean, you could definitely be creative here and do whatever you want on the stack. And I'm sure people already have, right? But yeah, talking about that, there's something interesting as well that is basically this is a compiler flag. And it's also in the notes that we wrote, but it's like f no omit frame pointer or omit frame pointer. And unfortunately, the problem here is that some compilers have this option of omitting frame pointers enabled by default, and many Linux distributions have this enabled. So what this means is that if you're writing some, for example, C or C++ application, and you have some native dependency on, I don't know, zlib or any other library that your operating system provides as a static or dynamic library, probably that library doesn't have frame pointers. And even if you compile your code with frame pointers, you need to use this information we're going to be talking about now to be able to get a full, reliable, correct stack trace. So yeah, it's complicated, and fortunately, there's 2 exceptions for this. So the Go engineers, even though they don't follow the x86 ABI, or they didn't used to follow it all the time, but they use frame pointers since, for the past couple of years, both on ARM64 and x86. And Apple has also been pretty good about this. So right now on their Apple Silicon machines, you must have frame pointers, or potentially your code is not going to run at all. I mean, it's going to run, but it's going to crash. So yeah, they acknowledge, right, how good it is to have reliable stack traces and very cheap stack walking, which is, yeah.
Yeah. Okay. Interesting. So, what if we don't have those frame pointers? What do we use instead? How do we work our way back through the stack?
Yeah, so there's this not little, there's this very advanced, very cool technology called DWARF. So DWARF is specification, and I guess there's a committee behind it that they provide a spec, and they provide with a format that allows for debugging. And they have three big pieces they cover. They cover type information. So for example, information about different structures, information about their classes, information about the different types of the different variables in the code. They cover line information, which is a way to map from addresses to function names, class names, line numbers, all this kind of stuff. That, by the way, we need to use in profilers, right, to get like the actual function names. And then they have unwind information, and this is called DWARF CFI. And
I mean, I guess actually, even if we were using frame pointers, the DWARF information is how we would go from like a location in memory to knowing what the function is called. Is that right?
Yeah, so exactly, that would be the line information, right? So out of these kind of three big areas that they cover, definitely you can, there's other ways to do it, but this is the most common and most reliable one, and it's the one that gives you not only the function names but also line numbers, right, which is incredibly important. So this is used by all these three pieces of debug information, and of course the bread and butter of how LLDB and GDB work, right? They use it all the time, and that's how they operate. So
and you also get that information if you're looking at bytecode, eBPF code as well. That I think it's still DWARF format information for.
Yeah, I think at some point maybe there's DWARF generated by the compiler, but I think I'm not super familiar with internals, but I think at some point it's converted to CTF. Sorry, not CTF. I mixed with the other one, with BTF.
BTF,
yeah. So BTF, as far as I know, it's both a line information and a type information alternative to DWARF that is more compact.
Yeah, the BTF definitely gives you the type information.
Yes.
I thought that we'll have to look it up to check. I think the line number stuff is DWARF format, but I might need to check.
Yeah, it moves so fast, right? Like there's so many things in the BPF ecosystem, so it's easy to not be up to date on everything. It's impossible for one single person. So yeah, let's talk a little bit about the DWARF CFI format and what it provides, right? So from a very like abstract perspective, it offers something that is very simple. It is a mapping for every single address in your program from your code. It gives you an action, and this action is a way for you to be able to recover a bunch of registers. And typically the registers you want to recover are the ones just before the current executing the function that is currently executing was called. So again, from an abstract perspective, it makes sense, right? It's kind of simple. So for example, it will show us things such as, okay, so there's they call it code location, so a new code location at this address. And when you're there, if you want to recover the stack pointer in the previous frame, you need to get the current RBP, the current frame pointer, and you need to add 18, and that's going to be it. For example, if you're in the other code location, you get this time RSP, the stack pointer, and you add 256. These are two random examples that I completely made up, and yeah, they are not from any binary. So this kind of makes sense, and you will be like, okay, this is easy, this is simple, I can deal with this, right? The problem is it goes a bit deeper than this, and sometimes it can tell you, okay, for this code location, you need to pop this thing from some stack that you need to store, and that's going to be the action you're going to have to do, right? So for that, you need to have a stack, and some other opcodes might tell you, oh, now you need to push the state, you're going to push it again, and then you're going to pop it here and pop it here, right? And that complicates things if we want to try to do this from BPF. But if we think about the last case, that one is even more challenging because in some code locations, you have what is called a dwarf expression, which is an arbitrary expression that is Turing complete that can tell you things such as get this register, multiply by this number shifted right by this other register. So not only you need to interpret this and evaluate it, but and of course parse it before, which is already like a bit of a challenge again from BPF if we were to do that. But also you need to do it while you're unwinding because it can ask you for current state, such as the registers, or to read some arbitrary memory location. So this is not something you can do without having the full state. You need to have the full state. You need to have the registers. You need to be able to access the memory and so on.
And you have to do that for every frame on the stack. So
yeah, of course, yeah. So these expressions, they are not that common. I mean, we've done a bunch of analysis on many executables that are in your typical Linux distribution, and they are rare. I mean, rare enough, but this is like again like very like implementation detail kind of thing, very low level detail. There's something in the notes. The problem here is that pretty much every single call to a dynamic executable, for example libc, goes through one of these. So you need to be able to at least be able to process some of these if you want to be able to tell the user, hey, your code right now is executing print, or it's executing exit, or it's executing kill, which is a bit of a challenge.
So at this point, I'm wondering now if we're trying to walk a stack from within a BPF program. There's a BPF helper called something like BPF get stack. Does that do all of this for you or not?
I wish. So what that helper does, it walks the stack, but it relies on frame pointers. And if there's no frame pointers available, it's probably going to produce a garbage result or an incomplete result. So it wouldn't be too weird to, for example, see 1 or 2 frames, but then you will miss all the other frames. And by the way, these 1 or 2 frames, the reason why they will show up is by pure chance. So they can also be wrong. The reason why this helper is still incredibly useful is because sometimes you do have frame pointers, for example, Go applications. So if you only care about Go, you're all good with that. You're totally fine. Or if you are Google or Facebook, because Google and Facebook internally compile everything with frame pointers. They really value being able to debug their systems, to understand their systems. And if, let's say, their biggest application that is serving user traffic or ads traffic is down, they really want to be able to debug it as soon as possible and get a stack trace reliably, really quick, right? So obviously you don't need to... Yeah, sorry.
That's really interesting that they choose to do that. It makes you wonder why everybody doesn't choose to do that in this day and age.
Yeah, this is an interesting thing as well, because they probably, obviously it depends on the application, but what openly both Google and Facebook say is that typically the cost of having frame pointers is around 1% in production, which if you think about it, 1% of the amount of machines they have is a ridiculous amount of money. But they still decide, they made the conscious decision not to disable them, because they know that then if, again, an application crashes, and they have really big C and C++ applications, right? Sometimes gigabytes of binary, of executables, then just having to parse this dwarf and one information and reliably do whatever they need to do is going to be so much more work, right? So also profiling is more, it could potentially be more expensive. Also, that's kind of why we can talk a bit about this later if you want, but that's why we started developing this in BPF, because the overhead of the current solutions to deal with this information without BPF is quite high. But yeah, it's very interesting, right? Like why the rest of us don't have frame pointers if they're so amazing, right? I personally compile all my applications with frame pointers, but and Fedora now has finally enabled them on the latest Fedora. I forgot which one it is, maybe 37, 38. But it's taking so much work by so many people, and a lot of engineers were against. And I'll be honest, even though I love frame pointers, some of them make good points, right? That they have some performance implications, and they don't want to. When someone compares Debian against Fedora, performance metrics are going to look different. And some people only care about performance; they don't care about observability of production systems, right?
Yeah. So good question here from Will. Can you tell whether, I think he means whether there's a frame pointer or whether frame pointers are available before you call. So if you're in a BPF program, you want to get the stack, can you just call BPF get stack? How do you know whether frame pointers are available?
Yes. So, okay, this is a very interesting question, and the answer is not quick, unfortunately, but I'll try to be as quick as possible. So, the only reliable way to do this will be to disassemble all the code and ensure that there's the setup of the frame pointer and the basically the dismantling of the frame pointer, right? This is called the epilogue and the prologue. Well, I think I forgot the names, but anyways, these two pieces of data. So you will have to disassemble all the text of your program. Obviously, this is not feasible in general. It's quite expensive, especially on x64, and we cannot do that on BPF either. So what we do is we again rely on heuristics. So what we do is we try to check if we can reach what we believe is the last frame, the bottom frame, as we call it. And if that is the case, we then run, we then use this helper, and we could have implemented it ourselves, but we use a helper. Otherwise, then we do other stuff, right? And we generate all this DWARF information, and we use this information to walk the stack. But there's something to say here, that is the get stack ID helper doesn't tell you if it was successful or not. And that's why we had to have some extra checks to know if it was gonna maybe succeed or no, right? But again, you rely sort of on heuristics. Unfortunately, it's not there. There's not a incredibly reliable way to do this without fully disassembling everything. So yeah, it's complicated. But with heuristics, we have checked our metrics, and we have like on billions of samples so far. We have a very good success rate of pretty much 100% when it comes to knowing if we need to use frame pointers or not. So these heuristics are pretty good, I would say.
Great. Yeah. So we'll follow it up with a few comments here saying it's easy to see, and I guess this is whether or not the frame pointers are there. You can see them in the object dump, which is
I don't disagree, right? It's not hard, but you need to do it, right? And again, this assembling takes CPU cycles. You will need to ensure that everything's done properly. There's many ways to do the same thing, right? So you need to, if you have a very simple pattern matcher, maybe it wouldn't do it properly, right? So yeah, definitely, like there's ways to do it. And I know that, I think, some debuggers such as GDB try to be super smart, and obviously they aggressively do whatever they need to do, like disassembling code to see, and GDB can switch from one mode to another if it needs to. So yeah, definitely it can be done, but I don't think for production use cases this is ideal.
Yeah. I will also bring up the Will's comment, basically saying thank you so much for the answer. So thank you for the question.
Anytime.
All right. So where were we? What have we got next?
Yeah. So so maybe we can talk a little bit about the how we overcame the whole thing about the stack machine, right, and the arbitrary expressions, right?
Let's do that.
So yeah, cool. So yeah, I mean, as we said before, right, in order to be able to process this, if we want to write like a library in user space to do this, you need to first write a parser for the data format. And this data format is very compact in the sense of it uses very few bytes, but it is not very friendly to access randomly, let's say. So basically, the whole way to give us this unwind information is through two types of bytecode. The bytecode that I was talking about, these arbitrary expressions, but even the non-arbitrary expressions, they're also defined with a bytecode. So you have to parse it, you have to evaluate it, and then once you do that, you can start doing things, right? Typically, for example, when you get an exception in C++, it uses all this machinery, so it won't do the whole work ahead of time. It would just try to parse the information that is needed. There's also some acceleration tables, but anyways, it's a lot of detail there, but it won't do all the work ahead of time. We'll just try to do as little work as possible. But the problem here in BPF, right, is, well, as probably most people listening here will know, BPF is a very restricted environment. You cannot really write Turing complete code in it. And I don't want to say the word impossible, but it's pretty much impossible to to do this from within BPF. So what we end up doing is one more layer of indirection, as usual in computer science. So we have our custom format that our whole project is open source and people can reuse it if they want, which is incredibly simple. So it is you can see it like as a big table that has two entries in each single row. One entry is the address, and then the other entry is this action that you need to do, this rule that you need to do. But we have made it very compact. So in terms of memory, we use more memory than DWARF, but but it's easy to access like randomly, right? So for example, this whole table is sorted by address, so we can just binary search over it. And the way we overcome the stack machine and arbitrary expressions is the stack machine, you don't really need to overcome it anymore, because that is to generate these actions. So once you evaluate it, you get proper results, and you can forget about the stack machine. And for the expressions,
well, so you just have to evaluate it once.
Yes, exactly.
Kind of
so once you evaluate it,
initialization time kind of thing.
Yes. So once you evaluate it, it gives you like a result, and that result you can use it, like for example in our case, in these different custom formats that is quite compact, right? For the expressions, it's a bit different, right? Because and again, it could be an expression, and we cannot support any expression. So in the future, if we want to support every single expression, we might try to implement a very limited evaluator in BPF. But what we did before even trying to do that was, because we knew it was going to be incredibly hard, was doing a little bit of baby data science. So again, download a lot of the executables in a bunch of distributions, check all the expressions that appear, and sort them by popularity, let's say, by how many times do they happen. And it turns out two expressions account for 60% of all the expressions that happen in the wilds. So these two expressions are the ones that I was talking about for PLT, procedure linkage tables, that typically are used for dynamic executables. So for example, libc and others, any executable you want that is dynamically linked. So what we do is that we basically hard code them. So we parse them and evaluate them in user space, and then in this special internal data structure that we have, we just store some special ID that we recognize in BPF. And in BPF, this code is also hard coded. These two expressions, I can point at them later in the code, in the notes, but it's two long expressions that are almost the same. So yeah, that's basically what we do. So then in BPF, we just have to have like a special case for one of the entries in this big binary search table.
Okay. So actually, one thing that we didn't mention, what is it that triggers the BPF program to run to do the stack up? I mean, you mentioned that you're doing, I think, 27 samples a second. Was that right?
Yeah.
What's the event that the BPF code is attached to?
Sure. So yeah, so we attach it right now to a perf event of type CPU cycles, which works great because it works even on machines that don't have hardware support. So typically there's some part of the processor that can trigger events, and some of these events are very interesting, like very low level of what's going on in the machine. But in this case, we use a software event, so it can run even in VMs. And what this does is, whenever it has like a counter internally, and whenever the technical name is overflow, but basically reach certain point, right? It then the kernel says, okay, now I need to execute this BPF program. And what the BPF program does is so it will run on that particular CPU, and then it will examine what is the process running there, and then it will try to start walking its stack. And yeah, the architecture is like very similar to many other BPF applications, right? We have, of course, BPF maps, a bunch of BPF programs, and then the user space driver that orchestrates everything and communicates with the BPF program and through maps, and also gets events through we use performance buffers right now because we want to be compatible with older kernels. But well, anyways, there's a bunch of methods of communication here. But yeah, it's basically originally kickstarted with a perf event.
Mm-hmm. Okay, great. So yeah, I guess one question is, what's the kind of performance overhead of running this? And does it make a difference depending on, let's say, what language your application is running in?
Yeah, no, for sure. So we need to get better metrics here. I have some metrics from a talk that we gave in FOSDEM, and I will get them right now. And I should probably put it in the document too. But the as a rule of thumb, if you run this on applications with frame pointers, the overhead of the BPF program executing is very, very minimal. I don't know how many nanoseconds it will take per frame. But even for DWARF, the performance overhead is really, really good, and that's for the one that have the numbers. It depends on the number of frames you have, right? Because it is proportional to how many frames you have in your application. But let me quickly get the metrics well, because I think it's super interesting, and it's still production safe, right? That's the most important thing for us, that we can execute it in production all the time. So the overhead is going to always be 1% or less. In our case, it's way less than 1% on the BPF side. 1% is like the whole system. And we do most of the work to convert the unwind information to our custom format in the beginning. So we do it once and we never do it again for that application while our agent runs. So and we only do it one time per unique executable. So for example, if you have 100 applications and 100 link libc, we only do the work once, of course.
Right. Yeah.
So yeah, we try to keep things as efficient as possible. And yeah, I guess the golden rule as well is to never disrupt the application that we're trying to observe, right?
Right. Yeah. And does it make a difference if it's interpreted rather than compiled languages?
Yeah, for sure. So this is something that we haven't integrated yet in Parca, but yeah, I work on a Ruby profiler like even before I joined this company called eBPF that works in a bit of a different way. So interpreted languages have the notion of a stack, right? But typically they are implemented in the heap of another runtime, like for example C or C++, right? So for example, in the case of Ruby, there's a bunch of data structures that Ruby written in C has allocated in using malloc or whatever they use to say, okay, now we have a frame here, and we're gonna push it to this other stack that we have allocated, and it creates, in this case, like a very big array. So that's their stack, right? So for example, in the case of our eBPF that we're planning to integrate and build new unwinders for other dynamic languages in the near future, we need to bake the same way we had to bake in the assumptions of the stack layouts from native applications in the work that I was talking about before. You need to do the same thing for Ruby, Python, and whatever dynamic language, with the difference that there's no guarantees on the layout, right? And it can change even across patch versions. This is a kind of an internal detail of the application. So yeah, it basically is a bit of a mess, but the idea is that every single version you want to support, if it changes internally, like a single structure that represents, for example, a frame internally becomes bigger, or the fields change order, you need to account for all of these. But fortunately, this doesn't happen a lot in practice. So for example, in eBPF, it supports like several Ruby versions with not a lot of work. But yeah, this is like something we are planning on adding. Right now, we support very well C, C++, Go, Rust, and pretty much any other application that is compiled and that follows the x86 API. There's some languages out there like Haskell that do not follow it very well. So we don't really support it well. But pretty much any other language works. And yeah, like the next goal for us is to continue supporting Java, Python, Ruby, and many others.
And you mentioned x86 architectures. Is it basically, the same but different in ARM?
Yes, it's pretty similar. And yeah, we're gonna start working on this very soon, because there's so many people right now moving to ARM64 because it has better performance for some applications. So yeah, definitely this is something we want to support, and hopefully it's also gonna make our development easier on Macs too. But yeah, this is something that Sumaira in our team is gonna start working on soon. So yeah, I'm super excited about that. It's gonna be great.
Amazing. I'm just going to say hi to a couple of folks who said hello earlier on. So hi to Vaishali from Berlin. Glad to hear it's sunny there. It's been absolutely throwing down with rain here in London. Just before we went live, it was almost inaudible in my room because I've got a flat roof. And also hi to Sebastian, who said a very nice thing about the eBPF book. So I'm glad you're enjoying it. It's great. And if you're out there watching and you're sort of sitting on a question and you're thinking, oh, I don't know, just type in your questions now, because we're 3/4 of an hour in. So we do, if you're gonna ask a question, now would be a great time to do it. Right, what else have we missed? What else haven't we covered today?
Yeah, so let me check. So there's some other, for example, I think talking about kernel support is interesting, right? There's some more things, but like we use kind of the bleeding edge of BPF features, or we would like to use them, but we try to be compatible with up to 3-4 years old. So there's a bunch of things that we don't do yet. And in general, like I think that's something that is interesting to talk about, right? Is the different challenges, right, of writing BPF applications that I'm sure that you're super familiar with, and that you have also suffered against the BPF verifier. Yes.
Okay. Yeah. So what kind of I mean, I guess you're trying to do some pretty complicated processing here, and relatively speaking, these are more complex BPF programs than most, I imagine. So what kind of challenges have you had getting that through the verifier?
Yeah, so for example, one of them is we use binary search, right, to find the right place where we have the unwind information for our right address. This was tricky to get the verifier to accept, and also not only is the amount of instructions that we had to use, but also the verifier internally has some sort of, I don't know what the actual name is, but let's say some sort of threshold that after that threshold it says, okay, I'm not going to try to verify anymore. I've been trying to verify this program for too long, right? So some sort of
complexity limit. Yeah.
Exactly.
Yeah.
So the complexity limit is something that we are quite familiar with. So I don't remember the exact number, but if with the current approach we have, I think that we were only able to unwind, I don't know if it's, 4 frames, which of course it's ridiculous, right? We wanted to unwind way more. And we managed to unwind now, like, I think it's 127 maximum, which is a pretty good number. I'm sure some applications, for them, it won't be enough, but for most, it should be. And we use a lot of tricks here. So we use, for example, BPF, tail calls. We also sometimes split our code in weird ways to get the verifier to accept it. Even though we try to support all kernels, and we were evaluating to support very old kernels, we realized.
How old are we talking here? Like,
yes. So right now, I kind of give you the lowest one we support, because we probably run on older than this, but we actively test. We have kernel tests, and the oldest we check is 5.4, which was released in November 2019. So it's old enough, right? It's almost 3 years and a half, right? If I'm not wrong, more or less, or 3 years.
Sounds about right.
Like
yes.
Yeah.
And I think some pretty interesting. I wouldn't be able to remember exactly what, but I think 5.4 was one of those releases that had quite a few interesting BPF changes in it. So
it had a lot of great stuff. Initially, when we started developing this, my target was to do everything to support 4.18, and it's definitely possible. But instead of using BPF tail calls, you would use other techniques that unfortunately are more expensive. So at some point we decided, okay, are we supporting older kernels, and then the overhead of our profiler running is slightly higher for all of our customers, including the ones running on very new kernels. So that was kind of the trade-off we made. We know this can be adapted to run on 4.18, which is, I think, 5 years old, something like that. But the thing is, because of also companies like yours in Cilium, right, the one that you work on, a lot of cloud providers have like pretty new kernels to have like the latest BPF features. So this is something that is highly beneficial for us. But so technically, like, not technically, but in practice, we test and make sure that everything runs 5.4 and above or greater. Yeah.
Okay, great. Yeah. And if people want to give it a try, how do they how can they try out Parca
Oh, sorry.
profiling?
Sorry, my friend Scott wants my attention. Sorry. He was quite aggressive about it. Yeah, so yeah, everything we do is open source. We have, well, we work in this project called Parca. The website is parca.dev, which is also on the notes. And yeah, please feel free to try it out. You can run both the agent, that is the part that has all these unwinders and BPF bits, and of course also the backend that receives these profiles, and you can visualize it there. So yeah, run it. Feel free to report backs. We also have a Discord that is linked on our website. So yeah, any feedback is greatly appreciated, and also if you want to contribute, please go for it. And especially if you're interested in low level programming, we do quite a bit of it. So yeah, more than happy to help, and the rest of the team as well.
Great. You've mentioned the show notes. I think it's in that corner, hackmd.io at echo-live. You'll find all of the show notes from all of the episodes. This is episode 89, and it should be the most recent one that you'll see there. And Javier has added lots of really good background information, lots of different links there. So if you're interested in all of this information about frame pointers and the DWARF information framework and Parca and all sorts of other details, there's lots of links there for you in the show notes. So do go check those out. All right. Any other sort of last things that you wanted to add? Or I think we've given people a pretty good tour. We've almost walked. We've walked through stack walking.
Yeah. No, I think that that's pretty much all. I guess that one small thing, right, is that this thing of using DWARF and one information has existed for a while, and it's used by other tools such as perf and others. And perf is great. I love it. I use it all the time. But one thing that we haven't discussed, why doing this in BPF makes sense, right? Because maybe some people will be like, oh, well, you're doing it in BPF because BPF is cool, and it's trendy, but it doesn't make sense. But in our case, it makes a lot of sense. Like first, because of the question you were asking before, right, about the event we are attaching us to. So the beautiful thing here is that you can develop anything, any kind of stack unwinder, and then you attach different events. So for example, perf events for cycles or for instructions or for L3 cache misses. And then suddenly you have a profiler for that event, or more complex stuff, network analysis or IO or system calls. So that is great, right? The other thing is the general idea that many people use BPF for, right? That BPF affords us because it makes the kernel programmable, which is having to do less work and being able to do things more efficiently. So the typical way you will implement something like this, but without BPF, would be to use a different system call that allows you to receive on every single sample, you will get the what would you get? You will get the whole stack of the process, not the stack trace, but the stack, right? The chunk of memory. You will get the whole stack and the registers. And if you think about it, if you have a machine with 20 CPUs, and this is something we have on the blog post that I'll link to with the proper calculation, if you have a machine with 20 CPUs, each of them at 19 times a second getting a sample, and assuming that the stack is a couple hundred kilobytes, which could definitely be, it's a lot of data that you're sending all the time. And not only you're sending all this data from kernel to user space, but you're sending it to another process, which means that maybe your security engineer won't love this, right? Because I don't know what's in my process stack. I don't know if I have, I don't know, a private key or something like that. So I'm sure, by the way, I don't know what I'm saying because I don't know anything about security. I'm sure the security frameworks try to keep things in the best places in memory. So, but the problem is, again, it's problematic, right? It's very easy to have like information that belongs to people, like names, emails, or whatever. And yeah, so the idea of doing this in BPF is that we never send the stack anywhere. We read it directly in BPF, right? We do whatever we need to do. And if we fail, we destroy everything. We never send it anywhere, sorry. We just drop the sample. So that's kind of one of the reasons why we wanted to do this in BPF, even though we had to work around a lot of things such as dwarf expressions.
Yeah, that totally makes sense. I mean, it's like a lot of the observability that people are implementing in eBPF. If you can collect the information in the kernel, filter down to the bits that you really want, and just discard everything else, then you've got a lot less information that you need to transfer to user space. And yeah, that's that, you know, it's one of the beauties of BPF. So totally makes sense. Great.
Exactly.
Fantastic. So I think we're getting pretty close to the top of the hour. I want to say this was really interesting. I always love looking at things like how are things laid out in memory, and what are we really doing with this? So yeah, this was really good for me. So with that, I'm just going to say thank you very much to the audience, first of all, for joining us today and for all your questions, and very much grateful to you, Javier, for joining us today and talking through stack walking with Parca. So thanks very much. And yeah, we will be back with eCHO next week. And yeah, see you then. Bye.
Bye.